Have you ever tried to fix something incredibly delicate, knowing that the very act of looking at it too closely might change or even break it? Imagine a tiny, intricate clockwork mechanism, so sensitive that shining a light on it alters its gears. In the quantum world, we face a similar, even more profound challenge. The good news is, yes, quantum errors absolutely can be corrected without directly measuring or disturbing the precious quantum information itself. This counterintuitive feat is a cornerstone of building reliable quantum computers. The core mechanism lies in what we call stabilizer measurements. Instead of directly observing the quantum state of a data qubit, which would instantly collapse its superposition or entanglement, we instead measure its symptoms or syndrome asterisk. Think of it like a doctor diagnosing a patient's illness by checking their temperature or blood pressure, rather than performing an invasive procedure to directly see the pathogen. We introduce auxiliary quantum bits, known as ancilla qubits. These ancilla qubits are carefully entangled with the data qubits. This entanglement allows the ancilla qubits to pick up information about whether an error has occurred, and even what type of error it is, such as a bit flip or a phase flip. Crucially, these measurements on the ancilla qubits only reveal information about the asterisk error type, not about the actual quantum data stored in the original qubits. This process effectively projects the overall system into a subspace that corresponds to a particular error, all while preserving the delicate superposition and entanglement of the underlying quantum information. So, how does this work in practice? First, the quantum information is encoded into what is called a logical qubit. This logical qubit is not a single physical qubit, but rather a combination of several physical qubits, usually 5 or more, that collectively representing the single unit of quantum information. Then, we use our ancilla qubits to perform those special stabilizer measurements across groups of these encoded physical qubits. The results of these ancilla measurements, called the error syndrome, are classical bits that tell us exactly which error occurred and where. With this classical information in hand, we can then apply a targeted quantum operation, such as a Pauli X, Y, or Z gate, to the affected physical qubit. This correction effectively reverses the error, restoring the logical qubit to its correct state, all without ever needing to directly inspect the original quantum data itself. This entire process is fundamental to achieving fault tolerance in quantum computing. This approach involves a special type of measurement known as quantum non-demolition measurement. This means the measurement itself does not alter the future evolution of the measured observable, or in our case, the quantum information it is meant to protect. It is an ingenious way to extract information about the system's integrity without disturbing its delicate quantum properties. Understanding this indirect error detection is key to appreciating how future large-scale quantum computers will be able to perform complex calculations despite being built from inherently noisy components. Ultimately, by mastering the art of correcting errors without direct measurement, we are not just fixing problems. We are actively building resilience into the very fabric of quantum computation. This clever dance of entanglement and indirect observation allows us to safeguard quantum information against environmental noise, paving the way for the robust and powerful quantum technologies of tomorrow.
If quantum tech fascinates you, like, subscribe, and keep exploring with us.